Now, in both of these cases, I know the average velocity, but I don't know anything really about instantaneous velocity. I know that every moment the velocity of that object is changing. That's why it's wacky, right? So here, from D to E, again, we were moving slow, and then suddenly we move fast. Here, somehow, we got launched pretty fast. Like, we're moving pretty, look at that kind of feel for that slope. We were moving really fast, and all of a sudden we started slowing down. Now, how that happened, don't worry about it. What I do want to tell you, though, is there is a way to find what we call instantaneous velocities at very particular points of time. Say I wanted to know velocity at 8.0 seconds. Now note, there's a little different notation. I'm not doing the average velocity between two times. I want to know the velocity at just one very specific time, at 8 seconds. And in order to answer this, you're going to have to employ a very particular method to solve. And we're going to do it kind of rough by hand, but using graphical techniques. So what you would do, if I wanted to know what the instantaneous velocity is at 8 seconds on this graph, I have to go from 8 seconds, see where at 8 seconds that would hit the graph, the line of motion, hit the graph. Now, before I get into this, let's back up. Remember back here, I wanted to know the instantaneous speed at 2 seconds. It was the same as the average because it was nice constant motion. It was a nice straight line, which was the slope of that line. So remember here, this was a nice constant and average velocity of positive 1.0 meters per second. So if it's 1 meter per second everywhere along the motion, the instantaneous velocity at 2 seconds would be that same 1 meter a second. Right? If I'm moving nice and constant, every moment it's the same exact value of speed, or velocity, I'm sorry. So that's going to give us a clue to how am I going to, well, so if it's a nice straight constant motion, I can find the instantaneous velocity because it's the same everywhere. But here, that's not the same everywhere. The motion is constantly changing. But that idea of slope is important. If you want to find the instantaneous velocity at a particular point on the graph, what you really truly need to do is take that point. Locate that point. All right, 8 seconds hitting the graph. I'm a little sideways here, but that's all right. Now, at that point, you want to draw a tangent line. A tangent line. Now remember, a tangent line is a little straight line that hits the curvature only at that one particular point. Now you may have done this with geometry class or trig class with circles, but you can do this with curves too. And so you want to draw a dotted line. I'm going to do this dotted line here. Well, it doesn't have to be dotted, but there has to be a line that's going to intersect. Not even intersect, it's just going to touch here and skim it only at that one particular point. So it's not going to cut or cross this blue line. It's just going to skim it at that one point. That's a tangent line. Now, tangent line is straight. And if it's a straight line on a distance time graph, I can find a value for velocity because remember, it's all about the slope, right? Remember, the average velocity formula here matched the slope. The average velocity formula here matched the slope. So I can find, and it won't be an average velocity though, but I can find a velocity using the tangent line. It will be the instantaneous velocity at that time. If I go here, my red marker is done, so let's go to green. All right, 7 seconds. And then let's go all the way up to like, I want to make it as big as possible. Let's go up to here. I think that'll work. All right, let's see if I can get it. There we go. Okay. So, I have my red line here. I'm going to do a rise over run here. I'm going to go all the way up to here. Go all the way over. I know it's a little messy, sorry. And it's not the best. I'm doing it by hand. You would use graph paper for this, okay? But I do have here a rise over run. And if I look at this rise, I go from 2 to 10. So we're going to say the rise, which is your delta y, or delta, actually, I'm sorry, it's your delta x. Delta x, which would be final minus initial, would be 10.0 minus 2.0. So that's a rise of 8.0. This rises, and I'm eyeing it up roughly, but I think that hits around, that's about at the 2 meter mark, and I think it's about the 10 meter mark where it hits here. Right? So that's a rise. Now the run, which would be my delta t, and that will be t2 minus t1. And if I look at those two times, down here I go from 7 to 10. And so if I do that rise over run, that'll be my instantaneous velocity. Velocity at 8 seconds. Okay? That would be, and this, by the way, this rise is positive, right? We are going upward. So it'll be the positive 8.0 over the, this is 3.0. And that would be an instantaneous velocity of 2 2/3, 2.7 meters per second. That would be this slope. So finding a speed at a moment in time, not an average between two times, but at that instant, that second, not even second, that blink of an eye, that microsecond, you need to find a tangent line. You need to mark that tangent line clearly so it only skims that one point on that graph, only there. You need to then make a large triangle, not a little small triangle, because if you do a small triangle for rise over run, you start estimating numbers too small and the error gets too great really fast. So the bigger the better. And you want to do the rise over run, which is equal to, change in distance over change in time for that particular line. And you can find the instantaneous velocity that way. Now, I'm going to quickly erase all this because you can find the instantaneous velocity at any point along the graph, really. What's an interesting point is, well, what's instantaneous velocity at 11 seconds? So if I go to 11 seconds, which should have been here, so I'm going to fake it a little bit. Because f is supposed to be over 11, so it doesn't quite, I'm faking a little bit, but at 11 seconds, I look at that point f and I want to draw my tangent line. Well, notice if I do that, my tangent line's pretty much a horizontal line. So velocity at 11 seconds equals, well, I can do, I guess, the tangent line, but I can't really do a slope of a horizontal line. What's the slope of a horizontal line? Nothing. So this would be 0 meters a second. So that's a possibility. Definitely. And then I could be even asked, beyond that. I could say, okay, well, what's going on at, say, 12 seconds? What's the instantaneous speed at 12 seconds? Well, again, I can I can do this process. go over here. Okay? And if I do this, I could draw a tangent line at this point at 12 seconds. I can do the slope, pick some points, find that rise over run. And you'll notice that this particular instantaneous velocity, now I'm not doing the math right now, but if you look at it, you should be able to see that's a negative slope. So your instantaneous velocity is going to be negative, which makes sense because you can see that it's kind of moving backwards. It's moving back towards the origin. Okay, so that was a lot. Process it, and trust me, you're going to get lots of practice on this. Thank you.